Hello and good evening. How are you? Hey, Shepard. Hi, Glory.
Hello,
If you don't,
Prof.
if you don't mind, turn on your cams. It's much more fun for me if I get to see your faces. There we
Hello,
go.
Prof.
Hi,
My
how's it going?
apologies for Monday lecture. I was having a challenge with network.
Oh, it happens. It happens. Were you able to watch the video?
I was still watching it right now. I
Oh, you
haven't
were.
finished. Yeah.
Okay.
Yeah.
Yeah, when you miss class like that, try and watch the video before our next class, because I always pick up where we left off, right? And there's two ways you can get it. I try to send out the link to YouTube, but even if I don't, I've already sent out the link to the playlist, and I always add the videos onto the YouTube playlist. And then the other place you can go is if you just go on to Moodle, I upload it right there on Moodle as well. So either one of those works. Just try and watch it before the next class, because otherwise you'll be a little bit lost. And I want everybody kind of on the same page whenever that's possible. But
Yes,
how are you following along? Is everything making sense?
yeah, everything is making sense except this lecture I missed. I have to take
Uh-huh.
time. Maybe I said 2 hours for that.
Okay. Okay. Do you feel like I'm going too fast, too slow? How do you feel about the pacing?
Yeah, I think the pace is actually good because it's giving us time to read on your own.
Okay.
Yeah.
Okay. Glory, how about you?
Uh, Prof, I actually need some more time in the calculation area. The aspect of calculation, I just need little time to understand more of this.
Okay.
The space is okay.
I'll go ahead and post some problem sets that'll give you a chance to work through them, and then you can look at the answers and see, if you're getting it right. And you'll see why we're doing these calculations, probably, hopefully, by the end of today. If we get through everything, you'll kind of see where this is leading and why it's actually interesting. Zach, have you, Zaku? Go ahead, turn on your cam if you don't mind. Oh, he's still connecting to audio. Do you, Zaku, can you turn on your cam? I'd like to be able to see folks if that's possible. Zaku?
Hello, sir. How are you?
I'm doing well. Could you turn on your cam? I like to see folks when we're in class together, if it's possible.
So unfortunately, my computer is not a frontal camera.
Oh, okay. Fair enough. Fair enough. But you can see me, correct? You're
Yes,
good with
of
that?
course.
Okay, good. Have you managed to watch all the class lectures up to today?
Yes, I'm working on it. I need to watch the lesson 8 and 9, but the other one I already watched it.
Okay, because yeah, if you can, it really helps to watch them, and I really suggest rewatching them. Like when
Yes.
I'm driving in the car, I'll often have, videos on so I can just listen to it over and over again. Just to, I pick up different things at different times.
A few days ago, I already submitted the peer teaching too. I don't know if it's late or what, but I
Um,
submitted 2 days ago.
so
And I'm
that's what
waiting
I
for
was
your
gonna,
report.
don't worry about it being late. That's what I was gonna talk to folks about today. I'm gonna go ahead and start grading and responding to them today and tomorrow.
Okay.
So not everybody has theirs in. I don't see yours up there post. You're talking about for justifying science. I do see that one. I'll get to that one today. The next one you want to do is the one that comes after that, which is indicators of climate change.
Yes, I will
And
do today.
okay, if you do that today, that would be great. And that will pretty much cover lectures 3, 4, 5, and 6. I should go over the temperature thermometer record and the various data sources. Okay, so we'll go ahead and get started because there's lots of fun things I want to talk about today. So what we talked about last time, here, let me center this. And oh, I should ask, do you all have the textbook? Shepard?
Yes,
do you have-
Prof, I do have the text. Yes, Prof.
Yes, I do.
Okay, read in the textbook. It's a really good textbook. I really suggest reading it. I tried to make my lectures so they really follow along with the textbook. Normally, I don't do that. I go off in my own direction, but since it's an online course, I'd like you to have a couple different ways to get at the same information. So please, if you can, do that. We're heading into we're covering chapter 4 now. So you want to read all the way through chapter 4. So last time we talked about Wien's displacement law. We were talking about blackbody radiation and what causes blackbody radiation. So as you warm something, the molecules start moving and the atoms start moving. And because they're surrounded by electrons, you get these moving electrons, which create little electromagnetic fields, which will send out photons. And so everything that's not at absolute zero is constantly streaming photons. And Wien's displacement law tells us what the peak wavelength of those photons are. And another thing we covered last time is just with photons, what the different wavelengths, what kinds of light it is, whether it's visible light, infrared, microwaves, etc. And so we can calculate what the peak intensity will be based on the temperature. That's all we need to know about the object is its temperature. And then using this formula over here, you can figure out what the peak wavelength will be. And I'm going to try for important formulas. I'm going to surround them with boxes. Those are things that you need to know. That'll probably be on the exams and stuff. But the other thing that we learned in looking at blackbody radiation and Wien's displacement law is this is just the peak wavelength. If you look at the actual emission spectrum, actually this is a power spectrum looking at the power of this stuff, for 3 different temperatures, you'll notice that as it gets warmer, the peak wavelength shifts to shorter wavelengths, okay? So it's higher in energy. And so I've got 300, 340, and 400K all shown here. And you can see that the peaks of these are shifting to the left, right, as the temperature increases. So it gets shorter as temperature increases. The other thing that this shows is the amount of power. So you can see that as the temperature increases, so we're going from blue to orange to green, you can see that the amount of power on this scale here is also increasing. In fact, if we look at the power radiated versus temperature, this is for any kind of blackbody object. So any object, as you go up in temperature, the power of the photons, that means the total number of photons per second. Remember, that's what power is. It's joules per second. So it's the energy per second coming out of these things is increases with temperature. And that's what you might expect. So based on this graph here, you can kind of tell that there's a mathematical relationship between the power emitted and its temperature. So we actually have something called the Stefan-Boltzmann relation. And here's another formula for us. And what this is saying is the power divided by the area, so power per unit area, is equal to sigma, which is just a constant. It's called the Stefan-Boltzmann constant, times temperature raised to the 4th power. So you take your temperature, raise it to the fourth power, and then multiply that by the Stefan-Boltzmann constant, and that will tell you the power per unit area. Okay. So let's just do an example of how one would use this. So if you wanted to calculate the energy being radiated by a 250K Blackbody, so it's a 250 Kelvin, not quite room temperature, so this is still kind of cold, right? We're going to use the Stefan-Boltzmann relation. All we need to know for this is the temperature, right? Temperature has to be in Kelvin. It already is, so we don't have to do any conversions. And so it's just the Stefan-Boltzmann constant times the temperature, where the temperature is raised to the fourth power. And an easy way to remember this constant is 5678. It's 5.67 raised to 10 to the minus 8. So there's 5, 6, 7, 8. And that units in that is watts per meter squared per Kelvin to the fourth. And so when we multiply this out for this 250K Blackbody, we get 221 watts per meter squared. And notice you're going to get a big number when you take something to the fourth power, but then you are going to be multiplying it by something that's 10 to the minus 8. So that's why it comes back down to a more reasonable number that we deal with. So for any object at 250K, this is what, minus 23 degrees Celsius, it's going to be radiating around 221 watts per meter squared. Note that this is giving the power by a unit area. So this is watts per meter. So this thing is shooting out stuff into, if you look at a square meter, there you'll be 221 watts will be passing into that square meter, or from that square meter. So as you might guess, you can calculate it for a whole physical object. So if we wanted to calculate the energy being radiated by a 250K sphere, then we need to know some stuff about the sphere, right? Because we're going to be calculating per unit area. But now we want to, if we multiply it by that area, we now know the total amount of power. So if we're talking about a sphere with a radius of 5, we're still going to use our Stefan-Boltzmann relationship, but we also need to, so we can go ahead and figure that out, and it comes out just like we did before. So here's the power radiated by this. And notice our units were in 221 watts per meter squared. So if we want to figure out the total power, the total number of watts, we need to multiply it by the area of the object, right? By the sphere. So the surface area of a sphere, you should know, is 4 pi r squared. And so if we just put 4 times pi, which is, we'll just use 3.14, and then our radius squared, our radius was 5 meters. So multiply that out. The total area of the sphere, it's a big sphere, it's 5 meters in radius, so 10 meters wide. The total area is 314. So if we multiply those two, right, because our total energy radiated is going to be the power per unit area times the area. So 221 times 314 is going to give us 69,394 watts. Okay. And we could just say 69.3 kilowatts if we wanted to shorten that. But so now that tells us if we got a sphere, it's at this temperature. Now we can tell the total amount of energy that we're getting off the sphere. So far, it may seem like we're doing a lot of different formulas. Here's our list of formulas. Here's Wien's displacement law. Now, I just rounded it up to 3,000, and you're free to do that for Wien's displacement. Just round these to numbers that are easy. Here's our Stefan Boltzmann relationship. You should know the surface areas for a sphere and a disk. And then our power, energy, and time relationship. In all those other relationships we've gotten before, you can always just rearrange this equation to solve for either energy or time if you've got power. Okay. We're all good on this. So if we know the temperature, we can tell how much power is being radiated. We good on that? Okay, you'll see where this is going. So something to think about is, what does it mean when you've got a black body and it's emitting photons? Okay, each photon is carrying away a small amount of energy away from the black body. Okay, and so what does that mean for the energy of the black body? If you got this black body and it's radiating energy, what does that tell you about the energy of the black body itself? It's just you, Shepard, and Zach. So one of you guys want to say something? Okay. So when a photon is emitted, when it's emitting this black body radiation, if it's carrying energy away from the black body, that must mean that the energy of the black body is now going down, right? Because you're taking energy away from it. And since temperature is a measure of internal energy, that means that as it emits photons, it should cool. Does that make sense? Okay.
Yeah.
So imagine I've got a small ball sitting in my living room. So size of a globe, okay? It's about 0.4 meter diameter, sitting in sitting in my living room. It's at room temperature. So we need to figure out how much total power it's radiating, right? And so again, we can use this relationship, the Stefan Boltzmann relationship, that the power per unit area is equal to the Stefan Boltzmann's constant times the temperature to the fourth. And then if we multiply that by the surface area of this diameter ball, then we should get the total power radiated, right? So our temperature is 300 K. We'll just use that as room temperature. Our radius is 0.2, because notice here we were given the diameter, so the radius is half that. And so just plug these numbers in, throw in your temperature, raise it to the fourth power, multiply it by the Stefan Boltzmann relationship, and then multiply it by the surface area. And what you'll get is the total power radiated is around 231 watts. Okay. So that means if this ball is radiating 231 watts at room temperature, that means that the ball is losing energy at a rate of 231 watts, right? Joules per second. So that means its internal energy is going down, right? So its temperature should be going down, right? Why, if I leave it in my room though, and I come back, I don't find this freezing sphere in my room. Why is that? Why doesn't it keep getting colder and colder? We know it's constantly radiating black body radiation. And so it should be losing energy. If it's losing internal energy, our measure of internal energy is temperature. So its temperature should be going down. I come back in 2 days, it's still at room temperature. Why is that? I need you to think about it. Why does it stay that way? Glory, what do you think?
Oh, Prof, sorry, I lost out at the beginning because of power challenge. I didn't get it.
Okay, well, I'll explain it pretty simple. So we know that black bodies, based on their temperature, radiate energy, right? From our last lecture, we looked at a couple different
Yes.
black bodies. We used Wien's displacement law to calculate the peak wavelength. So the peak wavelengths at different temperatures we can see. We know that, however, they actually radiated a range of wavelengths besides just the peak. And if you were to sum up all the photons at all these different wavelengths, that would be the total power emitted, okay? And so we know these things are glowing, and we've seen that you can actually, if you look at the temperature, this is looking at power, the amount of power emitted by these things as the temperature increases. And we can actually figure that out through the Stefan-Boltzmann relationship, which we talked about today. But if it's true that they're radiating these photons, each of these photons are carrying energy away with them, right? And so if they're carrying away energy with them, then that would mean that the emitter, the black body, should be losing energy. And internal energy, we know we measure through temperature. So it should be getting cooler. So we use this power relationship to calculate the power emitted for a small ball sitting at room temperature, and that was 231 watts, joules per second. Now we looked at it for this ball, 231. Okay. So we know that this thing is losing energy by radiating this energy out. And so the question is, why doesn't it get colder over time? So you got this object and it's radiating this energy through black body radiation. We can't see it because it's in the infrared. So why doesn't it get colder? Shepard, do you have any thoughts?
Because the room has a wider.
Because the room has what?
It has a wider range. It is not conceived as in spaces for radiation.
Okay, so right, the rest of the room is also radiating energy as well. All the objects in the room are glowing with the same black body radiation. And so if the temperature is staying the same, that means that you have to be putting energy back into the object, into this little sphere, and that's coming from the room. How much energy has to be going into the ball for it to stay the same temperature? If it's emitting 231 watts, how much energy has to be going into it? How much power has to be going into the ball to keep it at the same temperature?
It has to be double of their temperature.
So if something's losing something at 231 and you want it to stay the same, you need to add 231. So this is getting back to the fundamental principle that's going to really deal with the whole course, is this concept of energy balance. If your energy going out that it's radiating is equal to the energy that's going in, the net energy doesn't change, so the temperature won't change. Okay, so while this ball is radiating at 231 watts, it also has to be absorbing at 231 watts. Otherwise, the temperature would change. Right? If you're putting more energy into it, then it's letting out, then it's going to start gaining an energy. If it gains an energy, its temperature goes up. Because remember, temperature is our measure of internal energy, right? It's the average kinetic energy of the atoms and molecules within. So you put more energy in, molecules start moving faster. That means its temperature is higher. Okay, so this is what we call the energy balance condition. And this is what determines climate change, is energy in has to equal energy out for the temperature to stay the same. If the energy in is greater than the energy out, then the temperature is going to increase. And vice versa, if you have more energy going out than you have coming in, then the temperature is going to decrease. Okay, and this idea of energy balance is really what is going to determine stuff for our planet. Okay, and to give you an idea about warming, so say I take the same ball, but I stick it into the freezer. Okay, it's been in the freezer overnight. I take it out. What happens? Well, let's calculate the power that it's radiating. Again, we're going to use the Stefan-Boltzmann relationship, and we know the size of the ball. So we're going to fill all that stuff in, and our temperature in this case, coming out of the freezer, is at 255 instead of 300. And so when we calculate our watts, we're going to get that ball is radiating at 120 watts. Well, what's going to happen to the ball that I took out of the freezer? And if I just leave it in the middle of my room temperature room, what's going to happen to the temperature of that ball?
It's going to be losing.
So the temperature of the ball is going to go down. It's going to get colder. You take something out of the freezer that's cold. Does it get colder over time?
Get warmer.
It gets warmer, right?
It's warmer.
No,
Yeah.
it's be
Right.
getting warmer, I think.
How much? So that
Warmer,
means
yes.
energy is going into the ball, right? How much energy is going into the ball from our room, in our room temperature room? We already calculated that, right? Because when we calculated the ball at room temperature, the same temperature as the room, we calculated it was emitting at 231. So that means it had to be absorbing at 231 because the temperature was no longer changing. So that means our energy in is 231 and our energy out is only 120. And so that gives us a net. The energy is increasing by 111 watts, right? That will start. So our energy in is greater than our energy out. And so our temperature is going to increase. And it will keep increasing until finally it comes into balance where it's emitting, where it's absorbing as much as it's emitting. So if you take it out, it's only at 255. If it warms up to 260, it'll be emitting a little bit more, but not the same amount as what it would be at room temperature. So that means it's still taking in more energy. So its temperature will keep going up until finally it reaches room temperature. Now, if it goes any higher than that, then it will emit more than it will be taking in, and it'll come back down in temperature. And that's why everything in the room stays at the same temperature. Energy in has to equal energy out. That's our state of energy balance. Okay. And that's really, really important to understand, because when it reaches the state of energy balance, then its temperature remains constant. And if we want to talk about a warming world and climate change, we have to think about the planet as a whole and that system and how much energy it has, because we know that it's radiating energy out. So this brings us to our first climate models. You know, when we talked about the IPCC and we said, you know, they had climate models which were predicting how climate change, you know, was going to be in 10 years or 15 years. How do they do that? Right? Where do those models come from? Are they just extrapolating up a curve? No, that's not what they're doing. They're actually getting a lot more involved, thinking about the physics into it. So our climate is really an energy balance problem, okay? If the amount of energy going out from our planet equals the amount of energy coming in, then our planet should stay the same temperature. Just like our ball coming out of the freezer, it'll keep changing its temperature until finally energy out equals energy in, and then it'll stay static. So where does the Earth get its energy from?
The sun.
Yeah, so we all know that one. It gets its sun. So the energy in comes from the sun. The energy out, we've noticed from Blackbody radiation. Remember Wien's displacement law. If we're talking about things in the normal temperature range that, say, the Earth is right now, in our Wien's displacement law, most of our Blackbody radiation are in the infrared. It's not up to the visible range, right? So our Earth is going to be radiating in infrared. The light from the sun, however, is in the visible range. Okay, we looked at the curve for something that's 6,000 degrees hot, and that gives us, you know, the bulk of the photons coming from Blackbody that hot are in the visible range, which is why our sun is, you know, gives us the light that it does. Okay, so we can actually calculate how much light is coming from the sun. We actually have measured that. This is called the solar constant, or S. And so what we've measured for an object at Earth's orbit, the amount of sunlight, the power of the sunlight coming in is equivalent to about 1,360 watts per meter square. That's how much light is coming from the sun. This number is important to know, okay? This number is important to know. I'm going to highlight things in yellow that you should be remembering. So write this in your notes. Our solar constant, S, is 1,360 watts for every square meter. Now, if you're talking about a different star or different planets at different distances, the solar constant would be different. But for our sun, and at the distance of Earth orbit, that's about the amount of power that we're getting from the sun. So remember that guy. So now we need to think about how much light's actually falling on the Earth. How much of this power is being put into the Earth. And to get an idea of how to see that, put on this little graphic. So if the sun's light is here, you know, the sun can't shine on the opposite side of the Earth, right? It can only shine on one side of the Earth. And if you were to put a screen behind the Earth and it cast a shadow, that's actually the light that was blocked. So the light that's in the light that's not in the shadow is what landed on the Earth. Everything that went past is landed out here and it's lit up. So what we find is it's just a circle. So the area of the light hitting is just a circle with a radius equal to the radius of the Earth. Okay. So if our radius of the Earth is 6,400 kilometers, we know the area of a circle, pi r squared, and so we can figure out the total amount of power. So our solar constant is 1,360 watts for every meter squared. And the total amount of meters squared is pi times 6,400 squared. And so that gives us, now notice I needed to change kilometers to meters because our units are in watts and meters. So everything has to have the same units. And so that gives us about 1.75 times 10 to the 17 watts. That's how much energy is falling down onto the earth. Okay, and another way to put that, if we like, we can use terawatts. That's the same thing as 175,000 terawatts. An easier number to deal with. So that's how much energy is falling on the earth. Now, how much of it gets actually does all the light that's falling on the earth get absorbed? I'm asking you guys. Do you think all the light that's falling on the earth gets absorbed by it?
Not. I think so. Is yes.
Shepard, what do you think?
Prof, I don't think all of it gets absorbed.
Okay, what light do you think doesn't get absorbed? If it doesn't get absorbed, what's happening to it? It's not getting absorbed, it has to be reflected. So what do you think might be reflecting? This is an important climate change concept. So it's a lot of the light that shines on the earth, a vast majority is going to get absorbed, but some things reflect. We know that okay, if you were to go outside and there was and you're wearing a black shirt and somebody else is wearing a white shirt, what will you notice in summer? Which would you rather wear, a black shirt or a white shirt in summer?
Yes, Prof, of course, white.
Why?
Because white does not absorb much heat.
Absorb heat.
Right. So white reflects most light while black absorbs all light. At least that's the theory. So what kinds of things on the planet do you see are white? When you're looking at this globe on the
Water
screen.
body.
What?
The water body.
The water bodies, they're more blue. They look blue to me. What's all this
Then
white?
the clouds, Prof.
The clouds, right? What else?
Yeah,
might be
the
white?
clouds.
What else might
It means
be
it
white?
does not absorb much heat.
Right? What else might be white besides the clouds?
I think the land also absorbed the light.
The land will absorb the light, right? What on the land, is there ever anything white on land naturally? You guys probably don't see much of it. We call it snow or ice. You probably don't have a lot of it down there, right? And so if you look at the solar energy influx, okay, light will come down. If there's ice on the water, that's white, so it'll reflect that back up into space because it's reflecting visible light. So one of the assumptions that we're making is that visible light is transparent in our atmosphere. Our atmosphere is transparent to visible light. We talked about that last time, why humans see in the visible range. It's because that's the range in which electromagnetic radiation can pass through the atmosphere without any problem, so we can see things far away, right? So ice, clouds, glaciers, all of those things will reflect off the visible light and not absorb it. Turns out also aerosols in the air can also reflect some visible light, okay? They work a lot like the clouds do. If there's dust from a volcano, for example, and that spreads out in the atmosphere, that dust will reflect, it'll be white and will reflect some of the sun's light hitting the earth. So that light doesn't get absorbed, that just gets reflected and goes back out in space. We call the percentage of light reflected back into space, we call that the albedo. So the albedo is the percentage of photons reflected back into space, or the percentage of light reflected back into space. And we've measured that for the Earth, and currently our albedo is about 0.3. And there's no units there, it's just a percentage, right? So it's just a fraction. Okay. And so if we want to think of how much energy the Earth is absorbing from the sun, we have to take into account how much of that energy is being reflected back out, right? So we know the amount of power coming in, the total power coming from the sun. We know the radius of the circle for the Earth. And so we don't want to multiply it by the albedo because that's what's reflected. We want the stuff that's absorbed. So that's 1 minus the albedo. And that will tell us the energy in. Okay. So, here's our solar constant. Here's the area of the circle. That's how much light gets past the albedo. Okay. And just bear in mind that different planets have different albedos, but this is the Earth measured at this time. So we've figured out in our last problem how much power is landing on the Earth or is coming at the Earth's circle, and that's 175,000 terawatts. So how much is absorbed? We have to multiply that by 1 minus the albedo to tell us how much we're getting. And so that means a total of 122,000 terawatts of energy is what the sun is giving to the Earth. That's how much the Earth is absorbing. Okay. And so that means that the Earth is going to have to release that same amount of energy if it wants to stay the same temperature. Okay. Because remember our energy balance. If the planet's going to stay the same temperature, the energy in has to equal the energy out. Okay. So we have this relationship that we've developed for energy in. What I'm going to do in this, and what they do in the book, is they say, well, let's look at not the total energy absorbed by the Earth, but the energy absorbed by the Earth per unit area. So we're just going to take that energy in and divide it by the area. And you'll notice that when you do that, these terms cancel out and you're left with this. So the energy in per unit area is just the solar constant times 1 minus the albedo divided by 4. And this is an important relation we're going to be using in the rest of our class. And so we know our solar constant was 1360 divided by 4 times 1 minus 0.03. And what that gives us is the Earth is absorbing about 238 watts per square meter. Based on the sun and the albedo, that's how many watts per square meter. Okay. Now, if the surface acts like a black body, that means that every square meter has to be radiating or is absorbing 238 watts per meter. If we want the Earth to stay the same temperature, how much must that 1 meter square emit for it to stay the same temperature? It's got to be emitting the same amount, right? So if it's taking in 238 per square meter, then it's got to be emitting at 238 per square meter. Well, we know the formula that tells us what temperature you have to be to emit at 238 watts per square meter, right? So that's the Stefan-Boltzmann relationship. It gives us the power per area based on the temperature. So what temperature emits this kind of power? And if you go through the numbers, we're going to find, sorry about this. So if you set this relationship equal to 238, because we know that if 238 is coming in and landing on the surface, then it has to emit at 238 for the planet to stay the same temperature. So what emits at 238? You figure this thing out kind of backwards. You can divide both sides by the Stefan-Boltzmann constant, and then you that just gives you put your temperature on one side here. So that means you need to take the fourth root of this number. And when you plug in those numbers, that gives you around 255 Kelvin. So this is our first estimate. This is actually our first climate model, because what we're doing is we're estimating the temperature of the Earth based on the energy coming in. If we assume that we have to be in energy balance, what temperature would the Earth have to be to send an equal amount of energy out? So we use Stefan-Boltzmann to calculate the temperature at which we're getting the same wattage out. And our first initial estimate of what temperature the Earth needs to be or would be at is about 255 K. Our measured surface temperatures are about 15 Celsius. So, so that's about 288 K. So our estimate is about 33 Kelvin too low. So why is our initial estimate low? And that's because our model neglects having an atmosphere, because an atmosphere will do something. Okay. And that's what we're going to talk about next time, is what the atmosphere does. Okay. We know the atmosphere lets in visible light and is transparent to visible light, but is it transparent to infrared light? Because remember, all our emissions are in infrared. And so if something blocks those emissions, what does that mean for us, the pizza consumer? So just remember, our climate models are based on this idea of energy balance. We've got the climate we have because it allows us to satisfy the energy balance constraint. Okay, and so we got to think about how much energy is coming in, how much are we radiating out, and then finally what's happening to that radiated out energy. If it doesn't all get out into space, something will be different. This 255 is what it would be without any kind of atmosphere if it was just a solid rock with a 0.3 albedo floating in space. And so what we'll do is we'll add atmosphere onto this, and then hopefully we'll get a good gauge for why we have the temperature we do. And then we'll be able to tell, well, if you increase, say, carbon dioxide, which absorbs in the infrared, how much of a difference is that going to make in temperature? And so then we can now look at how much CO2 we're putting in the atmosphere and be able to predict exactly how the temperature will change. Now, I'm curious, but before we break, I'd just like to hear from you. Is this kind of stuff, are you interested in this kind of, you're all interested in climate change. Are you interested in understanding these models, or am I going off in a whole set of teaching that you're like, this isn't useful? So I'm curious to hear your feedback.
Yes, Prof, it is useful, although we need more time to learn this calculation.
Sure.
Yes, is it useful?
It's quite interesting, Prof. It's quite interesting because I'm like imagining the kind of waste, the kind of energy we need to emit in order to balance the temperature that we are having at the present moment. It's
Right.
it's quite interesting to know and to know how do we calculate to bring a balance
Right.
with the amount of energy. What can we do? How do we bring a balance to the earth and make sure that we are safe, both humans and animals in the atmosphere?
Right. And, when you think about like the albedo, for example, if we have a 0.3 albedo, that makes a big difference on how much energy we're actually getting from the sun, right? Because as opposed to getting 175,000 terawatts, we're only getting 122. If the albedo is just the amount of white stuff, if we lose our glaciers, if we lose snow, our albedo is going to change. If the amount of cloud cover changes in one particular direction versus another, our albedo will change, and that will change the amount of energy being absorbed by the Earth fairly large, right? So what if, say the glaciers start to go away? Okay, we're losing, how much are we losing per year? You guys should know that number. How much are we losing per year in ice? Let's say in Greenland.
Is it 1
Now, 141 megatons is in Antarctica. I think it's 271 is for Greenland. Okay, so we're losing that ice. How will that change the albedo? If we start to lose more ice, is the albedo going to be larger or smaller as we lose ice? Remember, the albedo is how much you're reflecting. Will reflect more into space or less into space if we lose ice?
If we lose our ice, it means we're going to reflect less.
Right, we're going to reflect less. So that means the albedo will
Yeah.
become a smaller number, which means when we're calculating how much energy is coming in, we're subtracting a smaller number that's being reflected. So as we lose ice, we're going to be getting more energy in, and we're already warming. So it's going to make it worse as opposed to better. And so there's all these different factors with climate change to think about. But once you get the physics behind everything, you understand why, and you can quantify how much it matters. So when you're coming up with your capstone projects on, what you want to do to fight climate change or mitigate a problem, you'll be able to think about the scale. Well, what scale is this going to affect climate change on? Example. But thank you all very much for your time and attention today.
I have a doubt.
Yes.
I want to know among absorption and the reflection, which of them is responsible for the blue color in the sky during the day?
The blue color in the sky has to deal with light scattering off of nitrogen molecules. We'll talk about that after we do this week and next. Right? We're going to get to it actually next week when we start talking about the composition of the atmosphere. Might even start talking about it on Friday, and I'll cover it a little bit more. But that's due to light scattering by certain types of molecules in the atmosphere that scatter some types of light better than others. And it scatters blue light, so we see the blue, while the rest of the stuff, just goes back.
Okay, thanks.
Great question, and we'll cover it more in depth. Everybody should watch all the videos, rewatch them a couple times so you get used to these concepts, hearing them over and over again. And I should have your responses to the last peer teaching, and by Friday, I'll be assigning a new one. Okay, everybody,
Thank you, Prof.
have a great day. Bye-bye.
Thank you. Bye.